So the big question, I think, is when we look at records like this, if we go back and show you one of our main records here from the Vostok Ice Core, if we look at a record like this, there's a couple questions in it. Specifically, I'm looking at the two curves on top. One is temperature, one is CO2. A big question that I think is brought up frequently when talking about climate change is whether or not CO2 drives climate, whether or not the amount of carbon in the atmosphere is important in driving climate. Okay, most people will say that carbon dioxide is not an important factor in climate. It occupies only 395 parts per million. It's minuscule. It has no power. Okay, that's an argument that's typically made. And you probably have a few ideas on how carbon by itself or CO2 by itself is not the end all, right? There are other properties, right, through feedbacks that are much more important. But one other point that people often point at is when they look at, these graphs, and this is sort of what you've probably seen in Inconvenient Truth, where they look at, look, CO2 is followed temperature through time, or vice versa. And actually the question when you look at the records here together is which one's leading which? What's the dog? Right? Which one's leading which here? Is CO2 leading temperature, or is temperature leading CO2? Or does it matter? Okay? If temperature is leading CO2, if it's warming up before CO2 goes up, is CO2 involved? And that's the argument that's been made quite a bit. Okay? And you might want to think about it. Is CO2 involved? Is it involved, really? If temperature goes up before CO2 goes up, is carbon dioxide? How is carbon related? Okay, so temperature could change. Temperature could warm, right? That would basically decrease this potential solubility of carbon in oceans, which would mean more carbon in the atmosphere. And if there's more carbon in the atmosphere, that's going to increase the long-wave trapping of outgoing long-wave radiation and have a positive feedback on climate. And also, Dane, you mentioned permafrost. So other sort of positive feedbacks, right? Positive feedbacks may help explain if temperature leads CO2, CO2 can still be involved. So the question here is how much should orbital cycles actually alter global temperatures? If we had a climate system that had no feedbacks, maybe it's just a planet with no oceans, just land and a non-interactive land. It's like asphalt. It's asphalt with different colors. It's painted asphalt. It has the right albedo, something like that. But it's not interactive. Okay? And orbital cycles are really just sort of changing the seasonal distribution of heating on our planet. If you integrate the net solar radiation between sort of the right sort of orbits for glacial advance versus the ones for glacial retreat, you get the same answer globally. Same net solar radiation. Or same downward solar radiation. Okay? It's just distributed differently seasonally. So by itself, orbital cycles are not going to do much to climate. They might change things by a couple degrees Celsius, and that's going to be very seasonally dependent. But because we have an interactive climate system, we have ocean vegetation, we have clouds, etc., water, we have carbon, and that makes things much more interesting. Okay? So, and people have done this, they've run sort of models of glacial interglacial cycles in a non-interactive atmosphere, and they see sort of net temperature changes globally that are nominal, averaged over the annual cycle. Right, averaged if you look at the mean annual temperature, it doesn't change much. But we know from our sort of paleo reconstructions of global temperature that the difference between global mean temperature during glacial periods and interglacial periods is about 6 to 8 degrees Celsius. During the last glacial maximum, right, 18,000 years ago, global mean temperatures were 6 to 8 degrees Celsius cooler than they are today. Doesn't mean everywhere they were 6 to 8 degrees cooler. Global average was 6 to 8 degrees cooler. Some places were much, much cooler, like high latitude sort of continental locations, much, much cooler. Okay, so this is telling us that orbital cycles by themselves are not going to do much to climate. It's feedbacks that are actually responsible in the manifestation of the sort of, significant changes in global climate. And again, we're looking at here global changes on the order of 6 to 8 degrees Celsius, which doesn't seem like, dramatically different. We know that day-to-day temperature changes can be quite dramatic. 6 to 8 degrees Celsius, that was a very different planet during the last glacial maximum than it is today. Very, very different. Here's again, this is the Vostok ice core. Again, we've seen this before, but now what's being shown is temperature and CO2 overlaid on top of one another with the scales adjusted. Okay. And so we can see they're very, very strongly correlated. The red line here shows atmospheric CO2, and it again goes between 180 parts per million and 280 parts per million. Here's today today's up here, right? The red line's way up here, and temperature has not responded yet to that time scale. Okay, but that's where we are today, just for reference point. And we can see that they're very well correlated, and if you want to look closely, you might see something that would suggest that temperature increases just a little bit before CO2. If you want to look closely and you look at the blue line versus the red line, you might see just a slight offset. You might see that. Okay, and there's actually some fairly new research that is going to basically tell you the opposite of what I'm about to tell you. But it's pretty new research, so we'll figure out if it's actually holds weight or not. But the new research actually suggests that over the past million years, during glacial interglacial cycles, that CO2 has actually led temperature. Okay, but from looking at the Vostok ice core and the Greenland ice core, and looking at the record that you can see in front of you, what it looks like is that temperature increased before CO2 increased. Might be a very different picture, but nonetheless, there's this controversy here about which leads which, and the reality is it doesn't matter. Because, in the absence of sort of an interactive climate system, these orbital cycles should not result in any significant change in global mean temperature. Seasonally, yes. Spatially and seasonally, yes. But globally, integrated over a long time period, no. Should balance out. Same sort of net input integrated over time. But what's really fascinating is that you do see this response in temperature, and it might be just enough to start to invoke changes in some of these feedback processes. And certainly what we're looking at here with these sort of rapid transitions, again, rapid in terms of historic time, is we're looking at positive feedbacks. Positive feedbacks, dramatic change between glacial and interglacial, right? Or between sort of interglacial and glacial. Negative feedbacks would result in this sort of stable state. Positive feedbacks result in sort of rapid change. Okay. The other interesting piece here is that if we look at the last interglacial, so here's the last interglacial 120,000 years ago. Okay. And the blue line here is temperature in degrees centigrade compared to sort of the late 20th century. And what you see here is that it was warmer than today. It was about a couple degrees warmer than today. And this is from this record in particular here is from the Vostok ice core. It looks like globally the last interglacial period was about 1 to 2 degrees Celsius warmer than today. But again, what's interesting is that CO2 levels were only 280 parts per million. Okay, they weren't 390 like they are today, or 395. So what that tells you is that, okay, CO2 is not necessarily responsible for why it was so much warmer during the last interglacial. Right? It's not CO2. So what else could it be? Figure in the world. But here's our last interglacial period. Okay, and here's our sort of June 65 degrees north solar radiation. And I think I did refer to this earlier. The last interglacial period was sort of synced up very nicely, such that coming out of the last interglacial period, we had much higher levels of solar radiation at 65 degrees north latitude. Yeah, it's sort of like this. Okay, it was basically an extended period where we had the right sort of orbits, such that the northern hemisphere was closer to the sun. The tilt was maximized, right? It was more exaggerated tilt. You can imagine the tilt being slightly more exaggerated. You'd have even more radiation in the northern hemisphere during summer. And those orbital parameters are quite effective at explaining why we would have a sort of extra warming during that period without seeing significantly more CO2. Which came first, the warming or the CO2? It looks like the warming came first from the Vostok and Greenland ice cores. The new stuff that's coming out now is saying the opposite, but I think it's not necessarily which came first. It's whether or not you can explain the sort of rapid transitions and rapid changes 6 to 8 degrees Celsius by just solar forcing alone. And the answer is you can't. You need to invoke feedbacks, and invariably those feedbacks are going to involve ice albedo feedback, carbon, and water vapor feedbacks. Okay, so again, that's telling us that feedbacks are really quite important in actually explaining changes in climate historically, and the sort of nice balance between negative feedbacks, positive feedbacks. When positive feedbacks win out, you start to see these rapid changes, and that's what we see in going from a glacial to an interglacial and vice versa.